Welcome to this explainer. Today, we're diving into the hidden architecture that's basically operating inside our devices every single day. We're talking about the invisible magic of algorithms, specifically ones that can discover the unknown and make sense of completely chaotic data, totally on their own without any human intervention. We're going to explore unsupervised machine learning, pattern discovery, and how it maps the completely unmapped territories of the digital world.
So just imagine trying to organize thousands of photos without a single label. Think about your phone's camera roll right now. No folders, no metadata, literally no location tags at all. If you were handed this raw pile of thousands of images, manually sorting them, recognizing faces or landscapes would take you weeks, right? Yet modern systems can make sense of this raw, chaotic data completely autonomously, in milliseconds. But how?
Okay, let's dive into this. Section 1. What is unsupervised learning?
Unsupervised machine learning is essentially a type of machine learning where the computer learns from data and finds hidden structures entirely without labeled answers. The absolute crucial point here is that there is zero ground truth given. The system acts as a completely independent explorer. There's no human guidance, no pre-programmed cheat sheets, just the machine, the raw data, and its own mathematical ability to find structure in the noise.
So to really grasp this, let's contrast it with supervised learning, which is the standard approach most people are familiar with. In supervised learning, you provide the data right alongside the exact expected output. Basically, you give the algorithm the specific target to hit. But unsupervised learning, it totally flips the script. You just input the raw data. The algorithm's job isn't to hit a predefined target, but to explore the topological space of that data and discover the inherent hidden patterns entirely on its own.
A great way to think about it is like organizing a super messy music playlist into genres without knowing any of the song names beforehand. Visualize a massive, unlabeled playlist on shuffle. As you listen, you naturally start grouping the heavy, fast-paced tracks into one mental bucket and the slow, acoustic tracks into another. You're clustering by sonic similarity, not by text labels. And that is precisely how these algorithms process complex data.
Moving right along, let's look at Section 2, how algorithms find patterns.
And this brilliantly illustrates the mechanics behind the curtain. To organize the vast unknown, algorithms generally rely on three primary techniques. First up is clustering, which divides data into groups based on inherent similarities. If customer purchasing behaviors share statistical traits, the algorithm automatically groups them together, making it the absolute backbone of modern customer segmentation. Then we have association, which maps relationships between distinct items, like noticing that a high volume of users who buy bread and butter also tend to buy milk, mapping that relationship without even knowing what the products actually are. Finally, there's dimensionality reduction. This technique strips away the noise, simplifying massive, highly complex datasets down to their principal variables. It keeps the critical info intact while drastically improving processing performance.
All right, let's speed things up and look at Section 3, real-life applications.
This invisible magic is constantly operating in the background of our digital routines. Take Netflix, for example, recommending similar shows. It's clustering your highly specific viewing habits with millions of others to accurately predict your next binge, completely bypassing the need for humans to manually categorize every nuance of a film.
But the stakes go way beyond entertainment, right? Banks rely on this to detect unusual transactions and spot fraud. Financial institutions can't possibly label every creative new type of fraud out there. Instead, the algorithm just establishes a baseline of your normal spending clusters. And the very moment a purchase deviates from that hidden pattern, the system immediately flags it.
Similarly, think about how Spotify creates those highly personalized music playlists. Tying it back to our earlier analogy, the platform groups tracks with shared audio properties right alongside users with similar listening behaviors. It's real-world pattern discovery, building perfectly curated digital audio experiences in real time.
And perhaps most critically of all, cybersecurity systems use it to detect suspicious activity instantly. Because the system discovers patterns independently, it is incredibly invaluable when humans don't already know what specific threats to look for, like zero-day threats. Hackers are constantly inventing new attack vectors. Unsupervised learning spots the network anomaly, the outlier, even if the security world has literally never seen that specific attack signature before. It's a huge deal.
Let's slow down for a reality check in Section 4, Advantages and Limitations. Now, while this technology is incredibly powerful, it definitely has real boundaries. On the plus side, its main advantage is the ability to explore vast data sets that would take humans lifetimes to process, finding hidden structures and working with unlabeled data that we would completely miss. But on the flip side, because it operates without labels, it suffers from the classic black box problem. The results can be notoriously difficult to interpret. Plus, an algorithm might find a mathematical pattern that is technically accurate but practically meaningless in the real world. So the machine has unbelievable mathematical processing power, but, well, zero common sense.
Unsupervised machine learning allows computers to map the unknown, powering everything from your camera roll to global cybersecurity. But it leaves us with one final, pretty provocative question. What other hidden patterns might algorithms be finding in your daily digital footprint right now? I mean, every click, stream, and purchase is unlabeled data just waiting to be explored. Thanks for joining me on this explainer. Keep questioning the tech around you, and I'll catch you next time.